my God. I think
Okay, hopefully that'll give you a chance to see how you're doing. Resonance, Zollner, mass spec. How we do? Lab this afternoon downstairs, 2:30. We'll do some review, a little bit of new material with the various handouts we have. After spring break, the lab, I'm pretty sure it's phenacetin, synthesis of phenacetin from acetaminophen, as listed on the syllabus. Substitution reaction after the break. Okay, we left off here, steric effects. We're looking at the nucleophile. The nucleophile. Just like with the electrophile, the thing with the leaving group, if it's crowded, it's going to be a tougher reaction for SN2. Same thing goes with the nucleophile. If it's crowded, tougher SN2. Amines. Primary, secondary, tertiary amine is most crowded with these wings on it, these alkyl substituents on it. Tertiary amine, pretty tough to do SN2. It will do an SN2, but it's tough. Actually, the tertiary amine is often used as a non-nucleophilic base. Non-nucleophilic. It tends to be non-nucleophilic. For E2 eliminations, we'll be covering E2. So you have this over spring break. I wanted to get it to you today. Our next handout, eliminations. We'll make two stacks. Please make sure I get the rest back. Often used as a base for E2 eliminations because it's non-nucleophilic. It doesn't like to do substitution reactions as a nucleophile. All right. Same thing goes with substitution next door to the atom. Now you can't put any more substituents on the oxygen in this guy. You can only have one substituent. Okay. If it had two, it wouldn't be an anion. But we have substituents next door. This carbon has one carbon, this carbon two, this carbon three. Substitution next door also affects it. So that's still this wing out here. And this guy actually is doesn't like to do SN2. It's a little bit too sterically hindered. Also a very good base for E2 elimination. We'll mention that when we start with that handout. When we get into there, I'll refer you back to these two comments right here. He said, remember when we said terbium oxide is good for E2? Right here. Okay. I already mentioned this. If a molecule attacks an H, we call it a base. If it attacks anything else, we call it a nucleophile. Okay? Very similar ideas. Usually base and nucleophilic strength go hand in hand, but not always. For example, terbium oxide is the strongest base up there. Of the three. Strongest base. You should know why. But it's the weakest nucleophile. Because nucleophile that's attacking a carbon like backside, steric hinder, it's very important there. When you attack an H, sterics doesn't matter because the H is so small. Sterics doesn't matter. Okay, let's look at resonance. This is a better nucleophile than this. All right, we got lone pairs here, right? Looks naked without lone pairs, doesn't it? Typically we want to show full structure when we have something charged. This is a weaker nucleophile because this oxygen is really not fully minus, is it? What's the charge of this oxygen doing? Partial minus. What's the charge of this oxygen? Yeah. They have the same exact charge. Right? Resonance structure, right? Electrons in, electrons out, right? True structure is a blend of these. It's a perfect blend. This anion is delocalized by resonance onto the other oxygen. What about this anion? Is it delocalized at all? Is it spread to another atom? Can you draw a resonance structure here? No. You can look at that two ways. Electrons in, electrons out. What are you going to move out? There's no pi bond to move out. In terms of you're just moving your arrows. Theoretically, well, there's no p orbital next door. And these electrons are not in p orbitals. All those electrons are in hybrid orbitals. I mean, this molecule has no p orbital at all. Resonance is a p orbital thing. That molecule cannot do resonance. No, that's the structure. There's no other funny business going on. That's the structure. So which is more reactive, a full minus or a partial minus? Full minus is going to be more reactive. Yes? Resonance delocalization spreads the charge out. It makes it less reactive as a nucleophile. It makes it more stable. That don't make it more reactive as a nucleophile. Something that's more stable tend to... Well, see, that's not always the case. I was about to say something more stable is going to be a worse nucleophile. Not always. Well, which is a better nucleophile, I minus or F minus? I minus or F minus? Better nucleophile. It's also the most stable. So you can't always say the most stable is the worst nucleophile. Okay. Which is a better nucleophile over here? Well, I already told you your answer. This one's a greater nucleophile than that one. Why? Why is this one a worse nucleophile? Is that lone pair just on that nitrogen? There's no charge here, but we have a lone pair. Or is that lone pair delocalized by resonance? You can draw a resonance structure here? Yeah. Can you draw a resonance structure here? No. No. Week 1, we learned that this lone pair is in a p orbital, where this lone pair is in a hybrid. It's in a p orbital doing resonance. And the resonance makes the lone pair... Actually, some of the electron density here is put here, here, and here. This comes from your resonance structures. Hybridization effects. Now, we looked at these things when we did acid-base chemistry. Which one's a better base? So this one. Better base and better nucleophile. Hybridization effects. This is a better nucleophile than this one. We don't have resonance in either one. Many beginning students think that this lone pair is somehow resonance because it's close to these pi bonds. It's not. This lone pair is in what type of orbital? Week 1, we said it would be in a sp2. Right? If you graph it, you're going to see it's sp2. If it's in sp2, you ain't doing any resonance with it. There's no resonance there or here. But the lone pairs are in different hybrids. This lone pair is in what type of orbital? We said that's sp2, where this one's what? sp3. There's your difference. Which one's going to be more reactive as a nucleophile? sp3. The sp2 nitrogen is a better parent. It holds the lone pair tighter. The sp2 orbital is 33% s, more s character. More s character, the electrons are closer to the nucleus. These electrons are not held as tight. They're out there ready, backside attack. Here I come, electrons. So that's analogous to saying, nitrogen's more nucleophilic than oxygen, because oxygen's a better parent. Well, in this case, this nitrogen's a better parent than this nitrogen. It's also a stronger base. Let's see how we're doing here. Rank the following in terms of nucleophilic strength. First group. What's the strongest nucleophile? Or maybe you want to start with saying what's the weakest nucleophile. Whatever works best. Ultimately, let's get these for one ranked. Anybody identify the worst or the best in those four? I think I see the worst. I see the worst easiest. What's the worst?
H2O.
H2O, why?
Because it doesn't ionize, so it's not strong.
Because it's neutral.
The opposite.
It's neutral. The others are all anions. Right? Anion, 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 neutral. Weakest to strongest. Yeah, that's the weakest. Neutral oxygen. I mean, the others are anions, right? This is organic chemistry. Spectator ions. Spectator ion. These are anions. Isn't the neutral a weaker nucleophile than anion? We said that above. Okay, which is weaker, hydroxide or acetate? You should know the structure of acetate, right? Which is weaker? Well, we just looked at that up there. Instead of O-ethyl, put OH, and that's acetate, which is weaker. There's acetate right up there. And we have OH, right? It's the same as that. It's just got an H instead of an ethyl. Which one was weaker? Acetate, because the charge is delocalized. Right? Charge delocalized. So that would be 2. We're going to... This is certainly stronger than that, but what about this? How about let's compare these two? S minus or O minus, which is going to be the strongest or weakest? S minus is stronger. They're both anions. Why is sulfur going to be stronger?
Because it's strong to electronegativity.
Because it's what?
It's strong to electronegativity.
That's more of a stability argument. S minus is more stable because it's larger. But we're not looking at stability, we're looking at nucleophilic strength. Does it go hand in hand or does it conflict? Which is better nucleophile? S minus or O minus? Difference is electronegativity, so which one's a better parent? Oxygen. Oxygen holds the lone pair tighter, so is that going to make it a better nucleophile or worse? Make it worse. Better nucleophile. Your body actually uses sulfur as a nucleophile a good bit. Okay? That's better than that, so if that's better than that, that's better than that. So it's basically like this. That's the best. That's better than this. That's better than that because this one's delocalized. And this is better than that because at least this one's an anion. A delocalized anion is, for us, is going to be more reactive than a neutral. I could perhaps give you some delocalized anion, but that would be getting into apples and oranges. But for us, we said anion's more nucleophilic than neutral, right? Previous page. How about down here? Which is the strongest or weakest down here? We got 5 down here. These are all anions, right? You got to see these as anions. Get rid of potassium. That's just a spectator. Potassium don't do any chemistry. That's ions. Group 1 ions. You learn Jenkins. They don't do anything. We call them spectator ions. They just watch what's going on. Right? What's the strongest or weakest there? Strongest is the nitrogen, right?
Yes.
Strongest. So I think we got to put a 5 here. It's strongest. Because we're going from weakest. What's the weakest?
F.
Yeah, that's the weakest. Then what? Then that one. Which is weaker between these? This is pretty straightforward here. Which is weakest? They're both oxygen and ions. What's the difference? They both have same hybridization. They're both oxygen. What's the difference? This has a T-butyl group. Big T-butyl group right there next door, like a big old wing. Sterically hindered. That's worse. So it'd be 3. Then this guy. That's the strongest, nitrogen. Right? You got R. RO minus versus RN minus. You got to have 2 R's here, or you got to have some H's or something. Right? Which is a stronger nucleophile. They're both anions. Difference is this one's oxygen. It's a better parent. It holds its electrons tighter. These electrons aren't held as tight. They're going to be able to react. Since they're both anions, ignore that. Ignore the fact that they're anions. That doesn't tell you anything. The difference is that this is a better parent, worse nucleophile. Right? Everything's there. Questions?
So until you get to those 2 oxygen groups, you can rank everything off of electronegativity.
Perhaps. I'd have to look at it. Is that what you see? Is that?
That's what I saw.
Okay, you might be right. Seems like it. Yeah, these 2 had same atom. What was the difference there? That was sterics here. The more sterically crowded thing is going to be a worse nucleophile. We said that at the top of the page. Yes. Summing it all up, what type of nucleophile can participate in an SN2 reaction? I don't know if this is exactly a summary, because we haven't said it yet, but once we say it, it's going to be our summary. You get what I'm saying? What type of nucleophile can participate in an SN2 reaction? Strong. Only strong nucleophiles. Got to be strong to participate in SN2. So what are strong nucleophiles? This was a relative ranking. Which ones are strong? The strong is very similar to when we said strong bases. What were strong bases? What do we call a strong base? Anions or sp3 nitrogen, sometimes sp2 nitrogen. Same thing for nucleophiles. Strong nucleophiles. Anions, sp3 nitrogen. Same thing. Things with high electron density. Anions. Also nitrogen, because a neutral nitrogen also has high electron density because nitrogen is such a bad parent. Lets its lone pair get out there to do stuff, even though it's not an anion. Anions, sp3 nitrogen. Are there any exceptions to that? Yes. Some anions that are so delocalized like sulfate, you say, oh, well, anion, strong nucleophile. No, it's not, because it's so delocalized that it's really not an anion. It's partial anion. And we also know that it's the conjugate base of a strong acid, so that means it's super stable. So that's kind of an exception. But we said everything has exceptions. Starting point anions, sp3 nitrogen. And that's stated over here, it looks like. Right? Okay, here we go. Which ones are strong? This propanol, is it strong? Strong nucleophile? Is it an anion? No. Is it sp3 nitrogen? No. Not strong. Strong? No. Strong? Yes. It's oxygen anion. Yes. Strong. Propylamine? Yes. sp3 nitrogen. Aniline? No? Strong or weak? It's not an sp3 nitrogen. When we say sp3, not the lone pair. I mean, you have to be, because if it's sp3, the lone pair has to be an sp3. No, this lone pair is in what type of orbital? Yes, a lone pair in a p orbital is typically not going to be or nucleophilic. It's busy doing resonance. Maybe if it was an anion, it might be. Certainly not neutral. It's not an sp3 nitrogen. And the lone pair in a p orbital typically ain't going to do anything ever. Happy doing resonance. KCN, one of my favorite reagents. I remember KC and the Sunshine Band from the 1970s?
Yeah, of course.
That's my boy. KC and the Sunshine Band? Strong or weak? What is this? Well, K is plus, so what is... That's plus, so Cn must be minus, right? Cyanide. It's a carbanion. Right? Strong or weak nucleophile? Strong. It's an anion. Water. Water's weak, right? Neither anion. There you go. Only the three I circled can do SN2 reactions as nucleophiles. So they're the only ones that are strong. Okay, let's look at some particular substitution reactions. Some more details, some specific examples. Everybody get a handout today? Please make sure I get those back. Okay, examples here. First, alkylation of oxygen. The first example would be alkylation of carboxylic acids. This is the carboxylic acid here, yep? Is that a good nucleophile for SN2? No, weak, bad nucleophile. But we can turn this into a good nucleophile. We can deprotonate it, turn it into the anion. This is now a good nucleophile. It's an anion. Well, what do we need to react this with to accomplish this? What do we need to react it with? Something that takes, what do we call something that takes H's? Oh, we need a base. What's your favorite base? Did someone say HCl? Favorite base? NaOH? Okay, we can use that. There's a variety of bases you can use here. Sodium hydroxide. Hydroxide will take the H. What will that produce? You should know your acid-base mechanism, be able to clearly see that you're going to get that plus what? Plus water. You got a sodium spectator that you can pair up with that. You're going to make the sodium carboxylate. But let's just ignore the sodium. Spectator ions, right? Get rid of them. Okay, here's your anion that you just formed. Good nucleophile. Now we can come in here with some type of carbon with a leaving group. And now we can do an SN2. These electrons come in here and kick that off.
I thought you just said on the last page that that's not a good nucleophile. It's steelophiles.
We didn't say that. We said it was not as good as the other one we showed. A relative comparison. Yeah, I mean, which is a better nucleophile? This one. Well, it's not delocalized. This is delocalized. But it's still an anion. And what are good nucleophiles? Anions and sp3 nitrogen. So, it's good. It's not the best, but it's still strong. And now we can come in here and write, what does that give? The oxygen now bonded to carbon, we just made that bond. And there you go. We made water over here. We want to completely balance all this. What else could we show over here? What was that? Very good. You can also show a sodium bromide as a fully balanced neutral outcome. Sodium ion and bromide ion. You can pair them up if you want. It's probably going to remain in solution, so it's going to remain ions. That doesn't mean we can't show it as sodium bromide. So what did we do? We just put an alkyl group on our oxygen. Used to be an H. Used to be an H under there. Now there's an ethyl. Okay? Ethyl's an alkyl. We alkylated, or we did an alkylation of the carboxylic acid. But first we had to make the good nucleophile. Your choice of base. This could have been a variety of things. It could have been KOH, or it could be other. It could be like sodium bicarbonate. There's a huge number of bases that can be used to accomplish that first step. You can even use it like ammonia here. Some type of nitrogen base. It's not even an anion. Okay? Good old-fashioned chemistry there, generating the strong nucleophile. Let's look at alcohols. Let's start with an alcohol. It's not as acidic. pKa of this is about what? Acid. About 4. This is about 16. Much less acidic. Because of that, thanks for choosing sodium hydroxide, because we used that up there and I got it shown here. Such a base is not going to deprotonate this. To make the anion. We know how to judge equilibrium. This is 16. What's the acid over here? Water, 16. Which side's favored, 16 or 16? Neither. Now you might say at equilibrium we got 50-50. Well, even that's not good because you're only converting half your molecules to the anion. Problem is, in practice, it won't be 50-50 typically. It'll be worse than that. To get a good outcome, practically, the difference in pKa's need to be at least 2 to 3 in your favor. 16 to 16 is no good. Thus, I'm saying that this base is not strong enough to remove this. It was up there, much more acidic. We need a stronger base or a different base. One thing we can do instead is use sodium metal. Now that's not a classical base. Doesn't even have a lone pair. But this will accomplish, we'll get the, what do you want to call this guy? This is an alcohol. What do you want to call this generic for this? It's RO minus, right? And then you got sodium with it. What do you want to call this generic? It's not an alcohol anymore. What do you call OH minus? Hydrogen hydroxide. Well, what do you want to call this? It's got an alkyl group instead of a hydrogen. Alkoxide, yes. Alkyl oxide, alkoxide, hydrogen oxide, hydroxide, okay? We can use sodium to form our alkoxide anion. Now this is actually a redox reaction, not a traditional acid-base, so we're not going to show any mechanism. Redox. And the fate of the hydrogen is it actually becomes hydrogen gas. It's redox. Here the sodium is 0, sodium metal. The sodium is now +1. So the sodium has been oxidized. What's been reduced? Well, elemental hydrogen, the H is 0. Elemental form, the oxidation state of the atom is 0. Here, though, it's +1. I don't know if you ever looked at doing oxidation states of covalence in Gen Chem. Perhaps not. But it's considered +1. So the hydrogen went from +1 to 0, so that is a reduction. So that's a redox. Probably a radical reaction. It's not a traditional acid-base mechanism. But we get what we want. We generate our alkoxide, sodium alkoxide. When you do this reaction, you take sodium and you put it in your alcohol, it'll start bubbling. What are the bubbles? Hydrogen gas bubbling out of it. If you put a balloon on your flasks, if you got enough sodium in there, it'll inflate the balloon. You'll get a balloon full of hydrogen. Here we're after this. But down the road, maybe you use the same reaction to generate hydrogen. And you focus on it. Typically when you do this, you just let that go out the hood. But sometimes you may want it. It's a way to generate hydrogen. Okay, but we made our alkoxide this way, so now we can do a reaction down below. So we turn the weak nucleophile into a strong nucleophile. Now we can come in with some type of carbon with a leaving group, and bam, kick you off. Now the oxygen is bonded to this carbon, and we just made that bond right there. And we also generated what along the way? Some sodium chloride. So there's your organic product. By the way, what have we made in these reactions? Up there we converted the acid, the carboxylic acid, into what type of functional group? Ester. Down here we converted the alcohol into what type of functional group? Ether. This is a very common way to make ethers. By alkylating the ethanol, the alcohol. Got to first make the alkoxide though. This is called a Williamson ether synthesis. Actually has a name where you start with the alcohol, make the anion, and then alkylate it. Right? We now have an extra alkyl group on the oxygen through this SN2. Phenols. Now phenols are more acidic than regular alcohols. pK of about 10. You can deprotonate them with sodium hydroxide. So the pKa, this is 10. Gonna make this plus water. That's 16. Which side is favored, 10 or 16? 16 is favored. This is favored by 10 to the 6th. That's good. Good to go. Let's get rid of that. Anion, right? Then these electrons, it's all kind of condensed. Methyl iodide. Boom, kick off the iodide. Very reactive, no sterics here. Those H's are real small. Put the methyl group on the oxygen. We converted the phenol into an ether. That's a Williamson ether synthesis. We can make rings this way. If you take this compound, treat it with sodium metal, you can get this cyclic ether. Or sodium bromide. What's going on here? What's sodium going to do to this? Sodium reacts with alcohols to make alkoxides. Right? If you want to completely balance all this out, what else can we show over here? Hydrogen gas? By the way, the reactions are not balanced. You get two H's over there, you're going to have two of these. Okay, I'm not balancing the reaction. Once this is a minus, what can it do? Bam, internal, kick you off. Just an internal SN2, which we would call a intramolecular SN2 reaction. And then gives that cyclic ether, yeah? Everybody seeing it? Williamson ether synthesis. You need to be able to go backwards. With organic 2, you'll do plenty of synthesis, which is where you're given some type of this and say, okay, give a synthesis of it. And this could be one synthesis. Here we go. Provide a synthesis of this. A Williamson ether synthesis. Whenever you do a Williamson ether synthesis, what do you start with? What type of compound do you start with?
Alcohol.
Alcohol, right?
Mm-hmm.
Then you start with an alcohol. But which alcohol? And then what is going to be the alkyl fragment that you bring in with the thing with the leaving group? There's actually two different Williamson ether syntheses you can show them. Show them both. And then we need to decide which one's going to be best. Which one would be the best reaction? Please do that on your own. We don't have time to get into it at this point. We'll look at it when we return. I'd recommend reading the chapter on Williamson ether synthesis in your textbook, the subchapter. Probably turn to the chapter on ethers, and they're probably going to tell you how to make ethers, and the first way to make them is going to be Williamson ether synthesis. Alkylation of sulfur. Your body uses sulfur a good bit. Just know that sulfur is it's the same chemistry. Okay? Same ideas we just showed on the previous page. I can also be a sulfur instead of an oxygen. The anion is better nucleophile. The exception though, a neutral sulfur, we call it a weak nucleophile because it's neutral. Tends to be pretty good though. Your body uses neutral sulfurs as nucleophile. Good bit. It's not an anion, but sulfur is not a good parent. It lets those electrons do things. All right? Where a neutral oxygen is a lousy nucleophile. Glutathione is a tripeptide that's in your body. Might be able to buy it over at the health food store too, I'm not sure. That reacts as a sacrificial nucleophile. Okay? For example, if you're exposed to some type of electrophilic toxin, like if you're exposed to methyl iodide, there's a variety of them. Very toxic because your DNA, which has like amino groups, come in here and kick that off. No sterics. Okay? This serves as your body's defense mechanism, though. It's got this good nucleophile. And this instead will come over here and keep this from happening. Keep this from happening. And we put a methyl on here. So what? Then this just gets washed out of the body, particularly because it's so ionic in the body. Okay, it's a sacrificial nucleophile. Sulfur. Anybody ever heard of mucomist? Nursing or doctor or anything? If you overdose on Tylenol, it converts to a very reactive species that reacts with nucleophiles. Okay, especially in your liver. But as an antidote, we give you this drug, and this comes in here and reacts instead. These are good nucleophiles. They react. You don't want your DNA or your proteins in your liver reacting. So this is an application of sulfur being a good nucleophile in the body using it. Have a safe break, guys. See some of you this afternoon.